Hello, everybody. I see the numbers are rolling in for all of our attendees joining us. Good afternoon and welcome to another meeting of the University of Chicago's Physical Science Division's seminar series on the origins of life. I'm Fred Chesla, professor and chair of the Department of the Geophysical Sciences, and I will be the host and MC for today's meeting. I'm going to introduce our speaker, Dr. Daniel Glavin, in just a moment, but I just wanted to remind everyone of the format here. While Danny is giving his talk, the Q&A button at the bottom of your Zoom screen will be open and a place where you can enter your questions. When the talk is over, I will be joined by some colleagues who I will introduce after the talk. We'll chat with Danny using the questions that have been submitted to identify key discussion points of interest. So with that, please make sure as questions occur to you, you enter them using the Q&A button. All right. To provide some context, you'll remember that last week we heard from Dr. Jenny Bergner, who spoke to us about the astronomical insights we're gaining as we study the chemical inventory and evolution that occurs in environments where we see stars and planets forming. Today, we'll be hearing about the insights we gained from looking at the records of formation of our own solar system and the detailed processing that shaped the building blocks of planets like Earth. As such, I'm very pleased to introduce our speaker this afternoon, Dr. Daniel Glavin, who is one of the world's leaders in the study of organic molecules and extraterrestrial samples. Danny began his scientific training at UC San Diego, receiving a bachelor's in physics and then a PhD in earth sciences from Scripps Institution of Oceanography. Now he's an astrobiologist and the Associate Director for Strategic Science at NASA Goddard Space Flight Center. I also want to say that Danny is a co-investigator and member of the OSIRIS-REx team, a spacecraft which just 2 weeks ago successfully collected a sample from the surface of asteroid Bennu, has stored it on board, and is poised to return it to Earth in the year 2023 for further study. So let me start by congratulating Danny and his colleagues on that success and welcome him as he talks to us today about meteorite delivery of prebiotic organics, an inventory for the origin of life. Danny, take it away.
Thank you for that very nice introduction, Fred. It's really an honor and a pleasure to be here today to talk to you about an important topic in astrobiology, and that's the prebiotic chemistry that led to the emergence of life. Let me see if I can figure out this screen sharing thing. Okay, I don't know if that's the right, having trouble getting in screen share mode here.
Yeah, we're seeing your...
From beginning. Let me try this again. Try this. Apologies.
No worries, thank you.
Well, it worked during the practice session.
I can vouch for that.
Yeah, try to go slideshow mode from beginning and it doesn't want to do that.
Maybe just hit start show and see if that works.
I don't see the start show button.
Down on the bottom right where it says 80, yeah.
Oh, let's see here. There we go. Does that look better?
Yes, it does.
Okay, thank you. Whew. Yeah, I was watching some of the previous speakers have similar trouble and I'm like, how could they not do this? It's easy. Okay, so let's get started here. So in this talk, I'm gonna really focus on what we've learned about primitive meteorites. This is like one of my favorite pictures of a carbonaceous chondrite in Antarctica, taken by Catherine Joy, I think in 2004. I can't remember the exact year, but these things really look like charcoal briquettes. You know, they're carbon rich and loaded with organic compounds. And again, these are the most primitive materials we have access to in our solar system to understand the chemistry that may have led to the origin of life on Earth and potentially elsewhere. So they truly are time capsules, frozen time capsules from the early solar system. So just a kind of a brief summary of how I got here, how I got into astrobiology. I didn't start out always wanting to do this. As Fred mentioned, I got my degree in physics at UC San Diego. This is one of my favorite pictures here, the Geisel library named after Theodore Geisel, the creator of Dr. Seuss. Spent a lot of time in there studying physics. Wasn't an easy subject for me. And really, even after I graduated, I didn't quite know what I wanted to do. I thought, astrophysics was kind of cool. I thought black holes were kind of cool. Maybe I could do something like that. But even in 1996, when I got my degree, I really had no idea. And it really wasn't until that summer when my applications for a variety of internships came back, and I was all over the board. I had applied to the State Department, UCLA physics summer program, and the one that I got accepted in was Jeff Beta's group from the Beta Lab at Scripps. Beautiful place to study. I love San Diego, so it was like a no-brainer for me to stay there. And started working in Jeff's lab as a physics guy. I was surprised why he selected me, because his emphasis is on organic geochemistry and amino acids. But when I talked to him later on in my career, he said, yeah, you were one of the more curious students in my earth science class. And so he recognized the name and took a chance on me, and I'm glad he did. And when things really changed for me, it was in August of that year. So I was in the summer NSCORT exobiology program at Scripps, working in Jeff's lab, and this huge announcement that really shook the astrobiology world, quite frankly, of evidence for life on Mars in this Martian meteorite, Allen Hills 8401. President Clinton even at the time said, maybe we're not alone, and if this pans out, it's a really big deal. So it made international news, and of course the worm-like feature in there still gets the attention. But I was really curious about the organics, and they had reported these polycyclic aromatic hydrocarbons in this rock and claimed that they were fingerprints of an ancient biota in this rock, so the chemical remnants. Now, Jeff was an expert in amino acids, and we had been working on other meteorites. And at the time of this announcement, of course, we requested a piece of this rock and got it. And we were very interested in looking at amino acids specifically. Jeff had always advocated that amino acids were a much better biomarker than polycyclic hydrocarbons, which are everywhere and very easy to form. We found the amino acids. That was pretty exciting. However, they looked just like the Antarctic ice, where this rock had been sitting for 13,000 years. And so unfortunately, we couldn't prove that there was any evidence for indigenous Martian life. But it did kind of occur to me that, this meteorite transport of the building blocks and potentially even life itself is important. Of course, you've all heard about the lithopanspermia theory that, meteorites hit Mars, blew off material, and seeded the Earth with the organics and potentially life. Turns out that, several metric tons of material from Mars has actually been delivered to the Earth over its history, and even continues today in the form of the Martian meteorites. And so, hey, maybe life did start on Mars and seeded the Earth, and we're all Martian, in fact, so that's been kind of a tagline that's been used. My take on panspermia is, okay, that's interesting. And, it's interesting to think about the planet swapping spit, if you will, right? But it still doesn't answer the ultimate question, which is, how did life start in the first place? And one way that we can get at that is by studying primitive meteorites to understand the chemistry of the early solar system. Another reason that we want to look towards meteorites is, like I said, these are the oldest materials that we have that are relatively pristine. We can't figure out how life started on Earth because that record has been destroyed, right? Through a combination of plate tectonics and erosion, and of course biology itself, which has just taken over every crevice and you can imagine on the Earth, including in the deep subsurface. It's everywhere, which is overprint any prebiotic chemical record. So we really do need to go out into the asteroid belt, look at comets and other fragments of these materials to understand what the chemistry was like that led to the emergence of life. And there are a variety of approaches to do this. Last week, Jenny Bergner gave a very nice talk about the chemistry of the protoplanetary disk and the types of things that can happen very early on, prior to even planetary formation. I'm going to focus primarily on this talk on the laboratory analyses that we're doing of materials from asteroids and comets materials that have been processed to some extent by aqueous alteration and thermal alteration, and talk about the chemistry that happened there. So this stuff includes materials from the interstellar medium and some of the ices and dust from the proto-solar disk, and really kind of brings it all together into a little chemical factory. And so that's what I'm going to talk about today primarily is what happened at that stage. But of course, this material would have been delivered to the Earth and seeding the Earth with the ingredients for life. And just to kind of touch on remote observations, it still amazes me what we can do just looking at the light in the infrared specifically. So over 200 molecules have been identified in the interstellar and circumstellar medium, which is just amazing. And that number is going to grow. Although, as Jenny pointed out last week, there are limits to this technique. Once you get to molecules with above 6 atoms, it gets tricky to detect these, and you run into signal to noise issues. And so I put together this kind of cartoon, if you will, just to kind of demonstrate the differences and what we can learn from spectroscopy versus lab measurements. And this was a measurement made by Scott Sanford at NASA Ames, where he compares an apple and an orange. And at least in the IR, in this frequency range, they look identical, right? But if you can bring these back in the lab and do chromatography and really analyze the makeup of these things, you can see, at least from this perspective, the sugar distribution is very different. Again, so this shows you the power of sample returning and getting materials back into the lab to really understand the full chemical complexity. I will point out that this isn't the end all. Liquid chromatography has its problems too, as I'll mention later. And even here you can see the question mark, right? So it's not that we can identify everything. It requires finding the right standard and really making the right guess about what that compound is. But nevertheless, it's important to get these materials back in the lab so you can really understand the chemistry. So just back to this slide again, focusing in on the lab analyses that we've done on meteorites, and also expect to do, as Fred mentioned, with samples that are returned from asteroid Bennu. I'll finish off with that. And just briefly, looking at, from my perspective, one of our biggest concerns is contamination, especially with meteorites that have fallen and hit the Earth, because they are contaminated and quite rapidly. And this kind of gives you an idea of the spectrum of difficulty, if you will, of trying to detect organic chemistry in samples that have been contaminated. So on the left is sort of a worst case, right? You've got the meteorite men digging up, big rocks from the soil, which is with bare hands, not how you'd want to do it. So that would be a challenging situation to be in. And then it gets better as you go to the right. We've analyzed meteorites from North Africa in the deserts there. We're always very careful. We collect some soil near the fall site as a control to understand the contamination, and there always is some, but that's a little better. The deserts are dry, and so there's less weathering and that kind of thing. And then even better is in Antarctica. And I had the opportunity to go on a meteorite collection campaign with ANSMET back in 2002, which was really exciting. That's me on the right, bagging up a meteorite. Interestingly enough, Dante Loretta is in the background. He's the principal investigator of OSIRIS-REx, and he was a big fan of the metal detector. So he would pick up iron meteorites and other things from the moraines using that technique. But again, these are really the cleanest samples, meteorites that we have available. Antarctica's, if not one of the most pristine environments on Earth. There are areas that we went to that had never been visited by humans before. Now, even better is if you can go to the place where these came from, in this case, asteroids, which OSIRIS-REx has successfully collected a sample and is getting ready to return to Earth. And we expect these to be very clean. And we've taken great care to document the contamination environment through witness coupons and other methods, which I'll talk about later. So this is really as good as it can get, if you will, with respect to looking at organic chemistry and understanding the contamination background. Okay, so analyzing these meteorites can really help us answer some key origin of life questions. I'm going to spend a lot of time today talking about chirality because that's my primary area of expertise. As you know, amino acids and sugars can basically come in mirror images, left and right-handed forms. And it's still a big mystery why life on Earth chose left-handed amino acids and proteins and enzymes and right-handed sugars, ribose and deoxyribose and RNA and DNA, when we know the opposite-handedness could function just as well. So there have actually been people who have built enzymes using right-handed amino acids, and they function just as well as the left-handed form. The problem is when you try to make them with both hands, right, left and right-handed forms, then those biopolymers don't function properly. So we really do think that homochirality is a fundamental property of all life, on Earth certainly, and also elsewhere. So again, why is life based on left amino acids and right-handed sugars, not the other way around? And also, what does this mean for looking for life outside of Earth using chirality? Is there life outside of Earth? Did it select the same handedness or not? And how do we think about that? And so meteorites have really provided us a wealth of information to address these questions. Okay, so why amino acids? Well, of course, the chirality thing is a big one. They are the building blocks of all proteins and enzymes in life. There are 20 of the standard L-alpha amino acids encoded in proteins. So actually 19 of those are chiral. The one achiral protein amino acid is glycine. And this is interesting. That's a picture of Stanley Miller at the University of Chicago working with Harold Urey back in, I think that picture was taken in 1953 when he was doing the first spark discharge experiment. I know Jack Shostak mentioned this briefly. But Stanley, tried to simulate the early Earth's atmosphere-ocean interaction, used spark to simulate lightning, and was able to create amino acids. So this really kind of set off the field of exobiology, if you will, the idea that you could make biologically relevant compounds from a non-biological gas mixture. And I'll point out that at the time, he found 5 amino acids using paper chromatography, which is really cool. Now, of course, we have much more advanced methods, but he measured 5. And to date, we've actually found 34 different amino acids in those experiments. So a lot more complexity than even Stanley knew about at the time. And yeah, it was an interesting story. Jeff Beta was cleaning up Stanley Miller's lab at UCSD and found some of these old residues from the original experiments, and also some residues of experiments that he never published on. One was called the volcanic spark discharge experiment. And yeah, so we analyzed the same residues that from the original experiment. So it was pretty special. It was neat to be involved with that. The other property that amino acids have is they have a lot of chemical diversity. So of course, the alpha hydrogen amino acids are the ones in proteins, but in meteorites, we find all sorts of structures, all different possible isomers, alpha, beta, gamma, straight chain, branch chain. So you have a tremendous amount of complexity, and we can use that structural diversity to figure out the origin and the mechanism of formation. So that's useful. And then of course, chirality, which I already mentioned. Okay, so before I get into specific meteorite results, I kind of wanted to do a quick Meteorite 101. There's actually a whole field on categorization and classification of meteorites, and it's actually quite complex, and I won't really touch on that here. But meteorites basically fall into 3 general groups: stony meteorites, irons, and stony irons. We like to focus on the stony meteorites because, again, these contain some of the most primitive materials. They have these chondrils, that's why they're called chondrites, that are really some of the earliest solids that condensed in the solar nebula. So ancient materials. And these are in contrast to the achondrites, which include the Mars, Moon, asteroid Vesta, Uralites, and these have been heavily processed and differentiated, heating and melting, etc. And that makes them a little more challenging to study. And certainly if we're interested in some of the earliest chemistry that took place, we don't want to focus on those. And within the chondrites, you have the carbonaceous chondrites, which is the picture I showed in the first slide. These are relatively rare, only about 4% of falls, but they're carbon rich. They contain 2 to 5 weight% of carbon and a lot of different organics. And even these can be broken down into 8 different groups. and actually 9 I'm showing here because there's one ungrouped type that I'll talk about, based on their mineralogy, elemental composition, etc. And then we classify these even differently by petrologic type, which has to do with the amount of alteration they experienced on the asteroid parent body. So type 3s in general, the CVs and CKs have experienced more heating, more thermal alteration. Those, turns out, aren't really great for original life studies because as you heat these things, you destroy a lot of the organic compounds. And we like to study the ones on the left side where you have lower temperatures and more aqueous alteration, which means more chemistry. And so I'm going to be talking about the CMs and one ungrouped carbonaceous chondrite today. So let's start with the CM. This is a CM type 2. Murchison meteorite's been moderately altered by aqueous alteration on the parent body. Fell back in 1969. And over 100 kilograms of this meteorite was recovered. So it's an amazing amount of material, actually. Most of the samples were found by these, they're called the Gillick brothers. I apologize, I forget their first names, but you see a picture of one of them down there, and they've got the meteorites spread out all over the post office. This is a small town, farming town. But again, what a wonderful, wonderful fall. I mean, this was a rare meteorite. Turned out Murchison is really the gold standard meteorite for organic studies, as I'll talk about here shortly. Of relevance to folks at University of Chicago. So a lot of this material actually ended up at the Chicago Field Museum, 52 kilograms or so. And some of it ended up at the Smithsonian here in Washington, DC as well. And I'm going to talk about analyses we've done on both samples. In particular, a really interesting one was one that we got from the University of Chicago a few years ago now. It was actually found by Robert Menard, who was cleaning up Cliff Matthews' research lab for him, and came across this basically a glass a desiccator that had these, he didn't really know what it was at the time, but these black rocks inside beakers that contained desiccant. And this desiccator had actually sealed shut over the years, frozen shut. It had to be broken open. It's unknown how long that these samples were in the desiccator, but we were fortunate enough to get one piece shown in the beaker there. Robert Menard sent it to us in 2015, 48-gram sample. And I have to say, to date, this is the cleanest Murchison sample that I've seen from an amino acid perspective. There's just very little evidence of any contamination. Part of me wonders if it's because of the storage conditions at the University of Chicago. And if you're interested in learning more about the results here, I'll refer you to a paper that came out in Meteorics and Planetary Science earlier this year. Okay, so as I mentioned, Murchison is the gold standard. It's out of all the carbonaceous chondrites, this is the one that everybody's been studying for the last 5 decades. And we've learned quite a bit. There's still a lot more to learn about it, but we've learned a lot about it. Turns out that most of the organic matter in this meteorite is in the form of an insoluble organic matter. So it very complex material, kind of looks like kerogen. It's these aromatic groups that are cross-linked, and they actually form in layers. Some people that work in this field actually think that this insoluble organic matter could act as an interesting template because it forms layers, and in between you could get some interesting, potentially prebiotic chemistry happening. What I'm going to focus on today is the soluble organic composition, and I have a list of all the different classes of organic compounds that have been detected, and it's amazing. I mean, you see fatty acids, right, up to, I think, carbon C12 is the highest. Of course, amino acids, we've identified 96 by name to date, probably a lot more in there. Polyols, sugars, just recently, last year, we found a ribose, which is the first detection of a biologically relevant bioessential sugar, which was very surprising because ribose is not very stable. So the fact that we saw it in Murchison was pretty amazing. And then, of course, purines, nucleobases, are also found in Murchison as well. So to date, 598 different soluble organic compounds have been identified, but as I mentioned, this is just scratching the surface. We now know from soluble organic analyses using high resolution mass spectrometry there are just peaks everywhere, like in every mass almost. This is work done by Philip Schmidt-Koplan over in Germany. And he estimates that there are probably millions of different chemical structures in these solvent-soluble components. So still have our work cut out for us. I don't think we'll ever completely understand the complexity here, but it's unbelievable. Okay, so back to amino acids now. This is the protocol that we use to study samples. Usually we take, small fragments, centimeter-sized pieces. We powder them just using a mortar and pestle, kind of to the consistency of a flour consistency. And then we heat it in water, distilled water, 100 degrees C for 24 hours. Again, this is to extract the water-soluble component. We actually have to take those extracts through a variety of purification steps to remove salts and other ions that can interfere with our analyses. And then we use two basic techniques that you can find in any organic chemistry lab: liquid chromatography, mass spectrometry, and gas chromatography, mass spectrometry. And we kind of use them for different purposes. So the liquid chromatography we use to do very sensitive measurements of trace organic compounds. We separate the amino acids and also measure their enantiomeric ratios. And then the gas chromatography, mass spectrometry measurements require more material. So we usually only do these on the meteorites that have a lot more abundances of these compounds. But we're able to measure their isotopic composition. And I'll explain to you why that is actually really an important part of figuring out where these compounds came from. So we can measure the carbon-13 to carbon-12 ratio, nitrogen-15 to 14 ratio, and the D to H ratio of individual amino acids. And this just kind of a bit of an eye chart here, but just to kind of give you an idea of the complexity here. This is a liquid chromatograph mass spectrometer run. On the bottom is retention time. So in general, the smaller molecules tend to elute first, and then the heavier stuff comes out later. And on the y-axis, we break it down by carbon number. So the simplest amino acid, glycine at the bottom, all the way up to 10 carbon amino acids. Now at that level, you're getting close to the signal and noise, but they're there. In our lab, we've identified all possible 2 to 5 carbon amino acids. For the 5 carbon amino acids, there are 23 different amino acid isomers and enantiomers, so quite a bit of complexity. And if you do the math and you figure out how many isomers are possible for a 10 carbon, you quickly get into the hundreds of amino acids are present in this meteorite. So as I pointed out, still a lot of work to do here, but the complexity is just impressive. Okay, so how do we get this kind of complexity? And as I mentioned earlier, the idea is that these asteroids they're really chemical factories. So you have these small bodies forming early on. They incorporate icy grains, both from interstellar environments and touch icy grains on the outside of the outer parts of the solar system. These come together to form larger bodies. And then you have short-lived radioisotopes like aluminum-26 and iron-60 that decay and release heat. And they can melt the ices and really drive aqueous alteration and heating, which we think is really what's driving a lot of the complexity we see in these aqueously altered meteorites. And one example of that is the Strecker cyanohydrin synthesis. I'm showing that mechanism here. But you could imagine, aldehydes and ketones potentially formed on icy grains, maybe in the interstellar medium, will rapidly form amino acids, alpha amino acids and alpha hydroxy acids just by exposure to liquid water. And we do this in the lab, and we see evidence for this in the meteorites. And I'll point out here that when we do these syntheses in the lab, we always form equal mixtures of left and right-handed forms. And so some of these results that I'm going to talk about where we see excesses of the left-handed form are unexpected and not what you'd predict from non-biological chemistry. Okay, and here we go. Let's get right into it. So this has been one of the biggest surprises, really, I would argue, in the field of prebiotic analyses of meteorites. It's these fairly large left-handed excesses. The original studies focused on isovaline and other alpha methyl amino acids, primarily because they're very rare in biology and on the Earth. And so they're unlikely to be contaminants. And so there was a lot of attention paid to these, and this particular one, isovaline. The other reason that these alpha methyl amino acids are interesting is they don't racemize. They don't convert rapidly from the left and right-handed form. It's just hard to pull off that methyl group versus protein amino acids. The alpha hydrogen is very easy to pluck away and racemize. And so what that means is that whatever the initial enantiomeric ratio was likely could have been preserved for long periods of time. So that was another reason to study this. And what we found in Murchison is that you get these excesses up to about 18.5%, I think is the record for Murchison. But the other surprising thing is you get a whole range. It's not constant. There's a lot of heterogeneity. And we think that that is due to the exposure of different parts of the meteorite to different levels of water. And I'll talk about why we think water is important to the story. But bottom line is a lot of heterogeneity in this. We don't know what the origin of this asymmetry is due to initially. It's not clear yet, but we know it's not terrestrial contamination. And as I alluded to just now, we think that these excesses are related to aqueous alteration. And the reason we think that is just from the data. Here I'm showing a variety of different carbonaceous chondrites on the bottom. On the right are the ones that have experienced the least amount of exposure to water on their parent asteroid. And as you go to the left, you get the type 1 meteorites that have experienced quite a bit of aqueous alteration. There appears to be a trend here. It's not perfect, and yeah, the error bars are kind of high, but this is definitely suggesting that water is playing some role in the amplification of the left-handed form of isovalene. So that's pretty cool. And then the other important part of this story is we have not found any de-isovalene excesses yet in any meteorite. EET 92042, we get a slight, potentially a slight de-excess error, but it's within the error. So right now, they're either racemic, equal mixtures, or we get left-handed excesses. So this, again, is pointing towards a potential solar system bias towards the left-handed form. Okay, so isovalene, that's interesting, but it's a non-protein amino acid. It's rare, maybe not really that interesting from an origin life perspective. But here we've recently have evidence that even some of the protein amino acids have large L excesses, and actually much larger than isovalene, up to about 60% excesses of the left-handed form. And this is just fascinating. So this was discovered back in 2012 by our group at Goddard, as well as Sandra Pizzarello. We looked at 2 different meteorites and again found L excesses of aspartic acid, glutamic acid, isoleucine. And then more recently, this really pristine University of Chicago Murchison sample is also showing evidence of a large L-glutamic acid excess. So this is real. Although I will point out that, you know, when you're working with protein amino acids, there needs to be extra caution with the interpretation, because they are common on Earth, and there is the potential for biological contamination. So to figure this out, we really have to measure the isotope ratios, the carbon-12 to carbon-13 ratio, D to H, et cetera. And we did that for these samples. And this kind of gives an illustration of why this is important here. This is a plot showing the D to H ratio and the carbon-13 to carbon-12 ratio expressed in delta notation. There's a kind of a complicated formula there on the bottom right for delta 13C in per mil. But basically what it's showing is that when you have organic compounds that are formed in extraterrestrial materials, especially in cold environments, they tend to favor the heavier form, the carbon-13 and the deuterium, compared to terrestrial organic matter, which is lighter. We say there's an isotopic fractionation effect here, where life tends to prefer the lighter isotope. And so if you can measure these, you can really start to pull out the sources. And this is just kind of a general rule of thumb. If the delta 13C value is above 0, usually that's a good indication that it's extraterrestrial in origin. We made those measurements. This is from the Tagish Lake meteorite. This is gas chromatography, isotope ratio, mass spec analysis, where we're basically here I'm showing the D-aspartic and L-aspartic acid peaks. Again, we get this large, 60% enantiomeric excess, which I think is still the record now. It's huge. But more importantly, the isotopic measurements, the carbon-13 to carbon-12 ratio, are showing that this stuff is not terrestrial. It was formed in a cold environment inside the parent asteroid. Plus 29 per mil is heavy. And so again, no indication of terrestrial contamination here. Of course, we were still being cautious, and we wanted to convince ourselves that there were no other compounds co-eluting with L-aspartic acid. And to do that, that's where you look at the mass spectrum. And we did that for both D and L-aspartic here, comparing to a pure standard. And again, the same mass peaks, no indication of any other peaks co-eluting or appearing. The same was true for L-aspartic acid. So again, this is about as definitive as you can get for a measurement of an L excess in a meteorite. And then just to kind of pile on here about why we think that this is not contamination, is that alanine, another very common protein amino acid, was also found in Tagish Lake, and it was found to be racemic, right? No enantiomeric excess, equal mixtures of left and right-handed form. So again, this is suggesting that there has not been significant protein amino acid contamination of this meteorite. Okay, so what's going on here? How are, why are we seeing L excesses in some amino acids and not others? How did this asymmetry even occur? Our current thinking right now is that polarized radiation had something to do with this. Probably very early on, our solar system was exposed to polarized radiation from a nearby O or B type star. If you look towards the Orion Nebula, you can see that the light, depending on the direction, can be polarized up to 17% polarization. Lab experiments have shown that if you expose icy grains containing amino acids to polarized radiation, you can preferentially destroy one enantiomer over the other. We've seen asymmetry on the order of 1 to 3% induced in this way. So we know from lab experiments that this is possible. And again, the meteorite evidence is telling us that, yeah, perhaps our solar system was exposed potentially to some polarized radiation, which bias things towards left-handed amino acids. But a word of caution here, this will explain up to 1 to 3% asymmetry, not 20, 30, 60% enantiomeric excesses. Those require an entirely different explanation. And here's what we think is going on. Kind of our best guess. This is what makes the most sense from what we see in the meteorites. I know Jack Shostak talked about this briefly in his first seminar, where he talked about physical processes of crushing and crystallization as a way of amplifying enantiomeric excesses. And indeed, in the lab, this has been shown to occur. If you can repeatedly dissolve and precipitate amino acids as crystals, you can actually amplify one enantiomer over the other. Now, interestingly enough, this only occurs with conglomerate forming amino acid crystals. So compounds like aspartic and glutamic acid, threonine, I didn't show the data, but we also see evidence for enantiomeric excesses there in isovaline. As opposed to racemic crystals like alanine, which we're finding is racemic in most meteorites, which through this process of dissolution, racemization, and precipitation, they become more racemic. So basically, in summary, this seems like a viable mechanism. We think that this could have occurred on the asteroid parent body during aqueous alteration. You could imagine potentially pulses of alteration occurring where you get dissolution. The amino acids could racemize and then precipitate. So you could have multiple episodes of that, perhaps driving the amplification of some amino acids, and then other amino acids like alanine, they would be driven towards a racemic mix. I will point out that this mechanism requires two things. One, it requires some initial asymmetry. You can't amplify if you start out with an equal mixture of left and right-handed forms. There has to be some initial asymmetry. Perhaps that's due to polarized radiation, some other mechanism, we're not sure, but you had to have started with some asymmetry. And then the aqueous alteration could amplify that on the parent body. The other problem that we have is you have to be able to racemize. So this doesn't really explain the isovaline results, right? Isovaline doesn't racemize. And so for this amplification to occur, you have to be able to convert from one form to the other in the aqueous phase. And isovaline doesn't do that very easily. So we're still kind of scratching our heads on isovaline, but this certainly explains the protein amino acid excesses that we've seen in meteorites. Okay, so what are the big implications here? Not only for the origin of homochirality, but the search for life as well. Well, as I mentioned before, still no D amino acid excesses in any meteorites. These are amino acids with a single asymmetric carbon. And again, this is pointing towards an inherent bias, at least in our solar system, towards L amino acid homochirality from the beginning. This also has implications for the search for life. Prior to looking at meteorites and seeing these L excesses, we'd assume that, hey, if you see any enantiomeric excesses, that's great evidence for life. But now we know from the meteorites that there are non-biological mechanisms that can do this, that can form these excesses. So that's problematic and certainly complicates the use of chirality as a biosignature on Mars or elsewhere. To address this, we actually have proposed some new criteria for using chirality as a biosignature. This was published in Chemical Reviews back in June. So I encourage you to, if you're interested in this topic, really check out this review paper. There's a lot of detail that I don't have time to get into in this seminar. We also talk about sugars as well. So I encourage you to take a look at that. But essentially, we've got this kind of Venn diagram illustration of how not only do you need asymmetry, but that asymmetry needs to show a light isotopic composition relative to the inorganic material in the meteorite, again, suggesting potentially a biological fractionation process. And we also need a simple distribution. Remember that from what we know about life, they're alpha isomers, alpha hydrogen isomers, and there's a limited set. Whereas in meteorites, we see, hundreds, all the possible isomers. So we're really looking for an amino acid signature where you have enantiomeric excesses, you have a simple distribution, isomeric preference, with a light isotopic composition. And we think with these three things, we can still use chirality as a biosignature. Okay, so let's look ahead towards future Mars exploration. This is a really exciting ESA Roscosmos mission called ExoMars. It was originally scheduled to launch this year, but coronavirus and other things made it really challenging to launch. So it's scheduled now for launch in 2022. And one of the cool things about this mission is it has a deep drill. And we haven't done this yet on Mars. All of our analyses have been scoops, within the upper 10 centimeters. This will be the first time that we can actually get deep into the surface. And the reason this is important is because the surface of Mars has just been blasted with ionizing radiation. It lacks a magnetic field. So cosmic rays, which we know can destroy organics, it's going to be tough going to try to detect that stuff in the near surface. But by drilling down, we can hopefully get it more, fresher material. One of the instruments on board ExoMars is called MoMA, the Mars Organic Molecule Analyzer. This was built and tested at NASA Goddard. It contains a gas chromatograph and a laser desorption MS capability. But related to this talk, it also contains a wet chemistry experiment using DMF-DMA, which actually reacts with amino acids and allows us to separate the left and right-handed forms using GCMS. And so I'm really excited about this experiment. This will be the first time we've ever measured, looked for amino acids, and if they're there, measured their chirality. However, I will point out that even in this case, we do not have the ability to measure the isotope, the isotopic composition of these amino acids. So if you think back to that Venn diagram, even if we find excesses, we may not be 100% sure until we're able to eventually measure those isotopes. And so that's why Mars sample return becomes more important, because now if you can bring these samples back, you have access to really the best analytical capability around the world. And the NASA Perseverance rover, which was able to get off this year in July, really exciting, scheduled to land on Mars on February 18th, is really the first leg of this Mars sample return campaign, which is a joint effort between ESA and NASA. And really, I think, we've got to do this. I think I've come to the point now, having worked both missions and also seeing the other side in the laboratory, that if we're looking for trace chemical evidence of life, we're going to need all the analytical capability possible. And so Mars 2020 will, I think, collect around 40 cores, seal them, leave them on the surface. a follow-up mission, which is a sample return lander. You see the rocket contains a rocket, and also a fetch rover will go out to collect the cores left by Perseverance, bring them back to the rocket. Those samples will be launched into orbit, has a capability to return 30 cores. And then we're going to have an orbiter provided by ESA called the Earth Return Orbiter that will rendezvous with that orbiting sample container, capture it, and then bring it back to Earth. If everything goes perfectly, we could have samples back from Mars on Earth in 2031. So fingers crossed that everything, a lot of things have to go right with this to get these samples back. Okay, so back to meteorites briefly. We can certainly learn a lot from meteorites. We already have, and I'm sure there's more discoveries to be had. But we don't always know where they came from, and that can be a problem. We know they're rapidly exposed to Earth's environment and contaminated after they fall, which can be problematic, especially for trying to determine, chiral excesses and asymmetry. And so sample return missions really allow us to bring back pristine materials from a place that we know where they came from, right? We know the source, and we can really put the whole story together. And we're hopeful, I'll talk about this in a minute with OSIRIS-REx, that some of the samples that we bring back may not be representative at all of what we have in our meteorite collection. So that makes them extra special. Okay, so you get these samples back, and as I mentioned before, sky's the limit on what you can do. Not only now, but 3 decades from now. These sample return missions, 3/4 of the sample gets archived for future generations. So there are people that aren't even born now that may be working on these samples we bring back from OSIRIS-REx and hopefully Mars as well. And just, simply put, there are instruments you can't fly on spacecraft. I mean, some such as the ALS synchrotron beamline for Zane's analysis, it's an entire building in and of itself. And so I'm a big fan of sample return. They take a lot of patience, they're complex, but ultimately, if you can get these samples back, just the amount of science that you gain from them is enormous. Okay, so let's talk about OSIRIS-REx. There's been a lot in the media about this mission lately. It's been quite a roller coaster of a ride for me personally as part of this mission. But we did it. We launched in 2016, took a couple years. We got to asteroid Bennu, which turned out to be a much scarier place than we ever imagined. We thought the surface would be something like a beach sand, but it turned out that there were these building-sized boulders everywhere. And we had to really rethink our strategy for collecting a sample. But we've done it, which is really exciting. So just to step back briefly here, why was asteroid Bennu selected? Well, it is a relatively rare type of asteroid. It's this B type of asteroid that we had evidence for was carbon rich, very dark, low albedo, dark carbon rich asteroid. And we think will be similar to the meteorites like Murchison and some of the other carbonaceous chondrites. The other reason we went there is that it's a potentially hazardous asteroid. So there's not a 0% chance that Bennu could actually hit the Earth in the late 22nd century. It's probably not going to happen, but we really wanted to go to asteroid Bennu and measure what's called the Yarkovsky effect. Turns out that the sunlight and the fact that this thing is rotating, there's a heating. So the sunlight hits and then it radiates heat in the infrared, which provides a very small force. So think like 3 grapes in your hand. That's the kind of force we're talking about. But over millions of years, that can have an effect on the orbit and change the orbit. And so we wanted to understand this Yarkovsky effect so we can better predict and model whether or not asteroids are going to be a threat in the future. Okay, so when we got to Bennu, we spent a couple years mapping the heck out of it, really to try to find the best sampling location, not only for a safety perspective, making sure we can find material that we can collect, but also from a science perspective. And one of the really great things was that the OSIRIS-REx visible and infrared spectrometer, OVIRS, built at Goddard, right away we saw that there are hydrated minerals all over Bennu. So that's the top curve in black, and looks similar to some of the CM carbonaceous chondrites that we also know have phyllosilicates and other clay mineral. So this was good news. It's volatile rich. And we also see indications of carbon, both in carbonate form and organic matter. And so that's good news. So once we saw this data, we realized, okay, we picked the right asteroid to answer these questions about prebiotic chemistry. So that was exciting. The sampling site was called Nightingale in the northern part of the asteroid, highlighted here. On the right, you see what's called a hazard map. The areas in green are good. These are areas that we can actually touch and not risk the spacecraft safety in the sampler arm. And then the areas in red are bad. One of these boulders, I can't remember which one. I think it was the one in the upper left, is called Mount Doom, was nicknamed Mount Doom because it's the size of a 2-story building. And so if we got anywhere near that, that would be scary. But it turned out we hit almost the bullseye right in the middle, which is amazing. I mean, the area of this, I think there's a scale bar, so 5 meters, and we hit our target within less than half a meter of the center. So just really amazing what the navigation folks did here. And I got a little video here, which hopefully will play. Okay, I'll just kind of let this run. You see OSIRIS-REx coming down from its 1 kilometer safe orbit with the arm extended, 11-foot arm. We blow nitrogen gas, which basically, so it kind of works the reverse of a vacuum, because a vacuum cleaner doesn't work when you're in vacuum, but by blowing this nitrogen, we can disturb the regolith and it gets captured in this collector, which kind of looks like a filter on an old 1957 Chevy or something like that. But when we did this, we filled the container. It was designed to collect up to, I think, 2 kilograms of material, and we filled it. And this just shows you the actual. So on the left, you see, all the stuff ejecting. We actually pushed our way down close to half a meter into the subsurface. So this material is real fluffy and friable. It's not like hard rock. The fact we were able to push our way down is pretty amazing. The only thing that stopped us from going deeper are the thrusters on the spacecraft that fired to get us out of there. So we overfilled the container, and then if you were following the media, you saw a lot of stuff about, oh my God, they're losing material. And indeed, when we pulled away, we saw particles emanating. The reason for that is that there's a mylar flap on the inside of the collector, and it was designed to be like a check valve, so it let material in but then not out. But we filled this with so much material that a couple particles had wedged themselves in between the mylar flap, and so it allowed material to escape. So we kind of went into a contingency plan where we had to quickly figure out how to get the TAGSAM head stowed and sealed in the sample return capsule. That all went very quickly and exactly as planned. And right now, the estimates of mass, we know we greatly exceeded our 60-gram requirement. It's probably more likely we've got 1 kilogram or more of material. So again, the amount of science that's going to come from this is just going to be amazing. Okay, so in March of this year, we'll start our way back to Earth. You might ask, well, why can't you just come back now? And again, this is just the amount of fuel and energy it takes, orbital dynamics. So we've got to wait till March to start our return. But then on September 24th, 2023, we will land in the Utah desert, Utah Test and Training Range. And I think this is still accurate. I think they actually know to the minute when this thing will land, 8:53 a.m. local time. So mark your calendars for that. For the first 6 months, we'll just be doing kind of a basic characterization of the material. A catalog will be published. So this material will be made available to the entire international science community. The samples will be curated under high purity nitrogen inside a special clean room at the NASA Johnson Space Center. And again, just really excited some of the measurements that will be made possible, especially now that we know that we've got a lot of mass available to us. The science team, we can use up to 25% of the sample mass. And then again, the remainder, the 75%, will be archived at Johnson Space Center for future generations. And then one of the things that I think makes this mission so special is this is the first time we really took contamination control and contamination knowledge seriously. It's not often that you get to do these asteroid sample return missions, and so we wanted to make sure that the collector was as clean as possible. This is the first time, to my knowledge, that a mission has actually controlled for amino acids specifically. So we had requirements to keep the amino acid levels low, and we measured witness materials throughout the entire assembly process to document that. We also have witness plates on the collector itself, which will be analyzed to understand contamination. We've looked at the hydrazine thruster gas. We've measured the nitrogen isotopes of the hydrazine. We've saved some of that residue for analysis potentially if needed in the future. And there's an extensive materials archive of various spacecraft components that will be saved, again, in case there's an issue with contamination. We want to try to trace it. So this is really, this whole program was really our insurance policy, if you will, for fully understanding the context of the samples. And you just don't have that with meteorites. They've got an unknown history, but with this sample, the history is going to be well known and well documented. Okay, and with that, I just want to thank you all for your attention. I hope I entertained you a little bit today, and I'm happy to take any questions.
All right, Danny, thank you very much. I will give you the single person clap for now. But that was a fantastic talk. Thank you for everything and explaining it all so clearly. We do have a couple of questions in the Q&A, and I encourage people who, as you're listening in or are interested, something occurs to you, please feel free to ask questions. I will be here as well. I have two colleagues joining me to discuss this with Danny. Joining me today is Jacob Waldbauer, who is a faculty member in the Department of Geophysical Sciences here at the University of Chicago. He's an expert on biogeochemical cycles here on Earth and the coevolution of life and their environments on Earth. Also, Dr. Jenny Bergner, who was last week's speaker, is joining us. Jenny is a Hubble-Sagan postdoctoral fellow here at U of C, and she is leading studies of the chemical evolution that occurs as stars and planets form. So as members of the panel, I was pleased to get both Jenny and Jake here, who kind of, as I said, bracket the expertise that Danny has and the timescale on which we're thinking about things. So Danny, I wanted to start off, I'll take liberties with asking the first question. You talked, your example of Murchison and the characterization that you've gone through and what was found there has been great. People have also talked a lot about comets being important in terms of astrobiological interest. Can you talk a little bit about what we know about organics and comets and how that compares to some of the things that we found in meteorites?
Yeah, great question. We certainly know quite a bit about comets. There's a whole spectroscopy taxonomy, if you will. Again, looking at the coma primarily and looking for lower molecular weight molecules. So we have a pretty good feeling there. As far as complex organics like amino acids, we actually don't know that much. We got some indications from the Stardust mission. This was the mission that returned dust particles from Comet Wilt 2. And we've looked at some of those grains and materials, and we see some indications for glycine, the simplest amino acid, and we were able to prove its origin by carbon isotopes. But that's about it. I mean, we don't have any evidence for any chiral molecules yet, at least from the samples returned from Stardust or spectroscopic measurements. The Rosetta spacecraft, which did a lot of, made a lot of measurements around Comet 67P recently. That mission came to an end, but did some really great science there. Also detected glycine and methylamine and ethylamine, but again, no chiral molecules. So yeah, it's a little bit frustrating to me. I think, comets, they certainly delivered water and probably a wealth of organic material to the Earth as well. But we just don't have the right samples yet to answer some of these questions. I'll just make a pitch. We really need a nucleus sample return mission. Go to a comet, not an asteroid, but a comet, and return a bulk sample, kind of like what we did for OSIRIS-REx, but at a comet. And I think we'll be able to answer much more about the organic complexity of the refractory material in the nucleus.
I'm going to ask a question that was submitted by one of the attendees, Philip Heck from the Field Museum. It's a great talk, and he was curious: is Tagish Lake still the least contaminated meteorite that has been collected or that has fallen?
Yeah, so it's certainly one of the least. Although I have to say, this new Murchison sample that we got from University of Chicago is right up there as far as how pristine it is. And this is really based on the enantiomeric ratio of alanine, which is racemic, both in Tagish Lake, but also in this Murchison sample. So yeah, it's starting to look like, it depends how these things are stored. I think curation is a big factor here. I know another meteorite that's very interesting, and Philip will know about this, and that's the Aguasarcas meteorite that fell in Costa Rica. And actually, we're collaborating with Philip on a sample of that. It looks Murchison-like, and it's an observed fall as well, fell in Costa Rica. And Philip was able to carve us out a sample from an interior piece. And so I'm optimistic that that may be fairly pristine as well. But yeah, Tagish Lake, some Murchison samples are certainly some of the most pristine carbonaceous chondrites that I've looked at from an organic perspective.
Great.
I'll turn it over. Jake, would you like to pose?
Yeah, so there's a question from Gijs Mulders, who's a postdoc here in geophysical sciences. Could life still form from the amino acids with the less abundant chirality? For example, assume a scenario with a small asymmetry between left and right-handed amino acids, say 60-40. Would there be a 40% probability that life uses right-handed amino acids, or do you think that probability would be much smaller, perhaps zero?
Yeah, I mean,
curious your take on that.
That's a great question. I don't know if I have the answer to that. I mean, you'd like to think if they're, with chemical evolution and the millions of years of prebiotic chemistry, that ultimately the one with more abundance would win out. But I can't say that with any kind of certainty. And some people have argued that, yeah, maybe on the early Earth, you had areas that picked up the right-handed form first, and some did the left-handed form, and ultimately by competition, the left went out. But that's a great question, and I don't really have a great answer, unfortunately.
Yeah, I guess from my perspective, I'm by no means an expert in this sort of thing. There may be some in the audience who are, but my understanding of this is a lot of the mechanisms for the arrival at full homochirality for life are fairly iterative. It's not a binary choice that gets made at one step, and so really if there is an evolvable system, and that's sort of the key supposition there, that a relatively small enantiomeric excess can be amplified sort of iteratively, progressively, as that system evolves and tends toward homochirality because it affords more catalytic efficiency or other kinds of advantages. So, yeah.
Great question.
Jenny, would you like to go ahead?
Sure. Yeah. So I will be reading the question of Lawrence and Narcita Lerner, who are curious, what about aldehydes and ketones as precursors of amino acids? Do we have characterizations of the more simple organics on meteorites?
Yeah, absolutely. We've made those measurements now. That's not something that we specialized in until recently, actually. So we have a colleague that works in our astrobiology lab, Jose Aponte, who's developed great methods for looking at aldehydes and ketones, as well as some of the carboxylic acids. So we're definitely expanding, and we do see them. They are present in these meteorites. So there's a lot more to the organic story besides amino acids. It's my particular bias, but we need to understand what those precursors look like. Perhaps some of the asymmetry originated in some of those. I know Sandra Pizzarello suggested that the aldehyde precursor for isoleucine was where the asymmetry occurred. And then when you did Strecker, you formed isoleucine that inherited that asymmetry from the aldehyde precursor. So they're definitely important to study as well.
Can I follow up by asking, are people studying like the isotopic kind of compositions, looking at where the different isotope labels are within the more complex molecules? And can you learn about the synthetic pathways that way?
Absolutely. One of the things that, so John Eiler's group is really working not only on studying the isotopic composition of the entire molecule, but different carbons within the molecule now they're able to isolate. And absolutely, you can learn a lot about the synthetic origins by doing that. So a very powerful technique. You need a lot of material for these isotopic measurements. So that's why, it gets me excited that we're bringing back potentially 1 kilogram of material, because, we're going to need mass to make some of these measurements and answer these tough questions. But yeah, absolutely, isotopes are really key for understanding how these compounds form.
So we also have a question from Yoav Kashiv. Said, if I understood correctly, the plot with the 3 intersecting circles that define detection of life is based on life on Earth, but wouldn't potential different forms of life be missed using these criteria?
Yeah, that's a great question as well. I mean, we've kind of made the assumption that homochirality, at least that part of it is important, because we've been unsuccessful making anything in the lab, right, that uses both left and right-handed forms. Not to say it's not possible. We think that that's a crucial thing. And then, yeah, you're right. A lot of our life detection approaches are heavily biased on what we understand about terrestrial biology. And that's really hard to get around. But I will say, we've learned a lot from meteorites, which I guess is an unbiased sample. This is just the chemistry that occurred in the early solar system, and it's producing certain types of compounds, amino acids. It's giving us hints about amplification mechanisms. Not all amino acids can be amplified. I mentioned one, alanine, is tough to do. And so I know I would be very interested if we went to Mars, brought a sample back, and found chiral, limited set of chiral molecules, and we saw large excesses in some of these amino acids that we don't have evidence for that happening in abiotic materials like meteorites. So I think that would be very compelling. But yeah, I mean, we're biased by our own experience. It's hard to get around that. So that's a good question.
I'm actually going to take the liberty of asking my own question too. So thinking back to what you were describing, asteroids being this organic factory where aqueous alteration is part of the story towards building what we're eventually seeing. The conditions that we would expect to see within an asteroid, have people talked about how that process would work on early terrestrial environments and whether or not the yield or the processes that we would get would be similar, or how would they be different, and how would that link to maybe what's ultimately used by biology?
Yeah. Thanks for bringing that up, Fred. Actually, when I did a practice run for this talk, I included that point specifically, that these types of processes could have happened on the early Earth. You can imagine a tidal region or a drying lake bed where you had multiple episodes of water drying out, crystallization. You could imagine these amplification mechanisms taking place on the early Earth as well. Meteorites just allow us to investigate natural cases of that, the ground truth, if you will. And we don't have that record of the Earth. But absolutely, there's no reason why those amplification mechanisms could not have occurred given the right environment and the right concentration of organics on the early Earth.
Jenny, would you like to ask your question?
Sure. So this is a question from Andrei Tokmakov. Is amino acid racemization as unlikely as you observe for isoleucine? I would expect that it is a slow process, i.e. isomerization is a rare event, but over the course of millennia, quite efficient. So do the timescales matter? Yeah,
they do. Isoleucine, alloisoleucine, like you said, it can racemize and epimerize. And it is a bit slower than aspartic acid, which is very fast. But again, that part of it doesn't bother me, at least for these amplification mechanisms, because if you can do that, then you have a reasonable explanation for how you can amplify through this crystallization. So you actually need racemization. It's very counterintuitive. When I actually didn't believe this at first when it was proposed. I'm like, that doesn't make any sense. But when you consider that some of these amino acids can only form crystals of one chirality or the other and not a mix, then it starts to make sense. But racemization rate is important. I would predict that the amino acids with the faster racemization rates would potentially amplify more if they're conglomerate forming crystals.
And if I could ask a question I had about this crystallization mechanism, is there any textual or other evidence in carbonaceous chondrites themselves for the presence of amino acid crystals, either extant or relic?
Yeah, the short answer is no, and I wish there was. And that's one of the biggest criticisms here is, do they even form crystals? Are the concentrations high enough? I mean, these lab experiments, they use a ton of this, powders, right? And you may not have that situation in an asteroid, in fairness. These are part per million levels. So, and to my knowledge, no, there has never been a detection of a crystal in a meteorite. What we do see, though, is we do see when we look at the lithology. So Sandra Pizzarella actually did a pretty good job of this with Murchison, but in the pieces where she saw the largest L-isovalent excess, it looked like they had more hydrated minerals, more clays, than pieces that didn't have it. So again, it's pointing towards water. We don't have all the answers here, but water seems to be pretty fundamental here, and there's certainly evidence for that. So whether it's crystallization or another mechanism we haven't thought of yet, you want to make sure that water is a part of the story.
We have a couple of exploration-related questions from the audience. One from Tommy Younce. Any plans to go to Venus, given recent discovery, perhaps of phosphine?
Yeah, so that phosphine debate has been interesting. And now it looks like there may not be phosphine detected. Again, this isn't my area of expertise, but it's going back and forth. It kind of reminds me of the methane debate, which is still raging on Mars. Although now with the Curiosity rover, we know there's methane, at least in the near surface. So I think it's going to take a mission to Venus to settle this, frankly, that can make that in situ measurement of phosphine. It could be there. There are other people who say, even if it's there, that's not proof of life. So there's that whole thing as well. I'll have to be frank, Venus is not one of the places that I would think would be a good place for life. But hey, in the upper atmosphere, much milder temperatures, it can't rule it out completely. So that's why we explore. You can have doubts, but we need missions. So I'm a big advocate of missions that can go to Venus and go through the atmosphere and measure the chemistry. It's been a while since that's been done. So probably as good of time as any to plan a Venus mission.
We had related to missions, people are very interested in OSIRIS-REx. And obviously in terms of astrobiology, there's the origin, but also the threat to life as well. So I'll modify the question that was submitted. The first was, are we demonstrating that we can, if needed, target an asteroid for destruction to save Earth if an asteroid is going to pose a threat? I'll let you answer that, and I'll follow up.
Yeah, so NASA actually has a whole planetary defense program. I'm not involved in that at all. But part of that is just making sure we can detect all the big asteroids that are a threat. I think above 140-meter diameter, that's when things get, could get dangerous if we get hit by something like that. There is a mission that's going to launch next year called DART, which is a double asteroid redirect test mission. It's going to a binary asteroid called Didymos. And I apologize, I can't remember. I think each of the asteroids have a name, but the spacecraft is actually going to intentionally impact one of the asteroids in that binary system and look for the effect on the other one, the gravitational perturbation from that. Basically see if we can move an asteroid and detect it by a large impact. So it's not a nuclear missile or anything like that. It's just a spacecraft, hitting the surface. But that'll be kind of the first mission that I'm aware of that's going to kind of look at that. One of the fears is, if an asteroid's coming and you blow it up Armageddon style with a bomb, that it's, instead of a bullet, you're going to be hit by a shotgun, right? You're not going to really change the direction of the orbit. It's going to hit the Earth, but a lot of pieces are going to hit. And so the strategy is try to get there early and figure out ways to nudge it just enough so that it doesn't cross, the Earth's orbit when we're at that location. And so I think that's probably going to be the strategy. I think if bombs go off, it's going to be try to detect it early on and set something off nearby that could potentially impart a force on it. But again, the more time you have that you know that it's going to hit, the more you can do to try to perturb that. And again, that's why OSIRIS-REx really, part of that was understanding the Yarkovsky effect and just seeing how the sun itself can change the orbit so we can get better at our predictions as well.
So going back to OSIRIS-REx, one of the questions I think, I mean, as you said in your talk, studying meteorites, is fascinating in terms of the array of organics that we're finding. And so this is really exciting with OSIRIS-REx to have some context from which we're going to be understanding the samples. Given the diversity of organic inventories that we see in meteorites, it would be interesting. Do you think what you'll see with Bennu, and I invite you to speculate freely here, but do you think what you're going to see with these samples from Bennu are going to be completely different from what we've seen elsewhere? Do you think you would have gotten something, if you targeted a different asteroid, you might end up telling a completely different story? Just talk a little bit about that.
Yeah, so there's really two parts of that. Part of the OREX mission was to kind of serve as a ground truth, because we have the spectroscopy measurements of the asteroid, and now we'll have the samples back that we can analyze in the lab. And so this kind of opens up a whole new field of asteroid spectroscopy and the calibration, really, right? So that we can make more sense of spectra, because we can't go to every asteroid and bring samples back. It would just not going to happen. As far as do I think that the samples will be different? Starting to lean towards yes, primarily these thermal inertia measurements and the fact that it's so friable and fluffy. It's unlikely that even if this stuff hit the Earth, that it would survive atmospheric entry and breakup. So there's some on the team that think that we wouldn't find an intact meteorite that's of Bennu-like, at least the surface of Bennu. So in that sense, it's probably unlike anything in our collection. I would be shocked if we didn't see organic compounds based on the organic carbon detections and the 3.4 micron feature we see in the IR. I would be surprised. If it looks different than meteorites in our collection, it's possible. It could look similar to the CMs, Tagish Lake, CI spectrally. It kind of looks like a CI or CM that's been aqueously altered. So if it does look like that, we've got a good story. If it doesn't look like that, we're going to have to rethink things. The only other thing I'll add is that even in the meteorite business, every single meteorite I've analyzed there's been something quirky or unique or different. Never seen two that are exactly identical. So in that sense, I expect to be surprised when we analyze Bennu materials.
I have a question from Kashiv. At the beginning of the talk, you mentioned the 1996 paper that claimed potential detection of fossilized life in a Martian meteorite, ALH 84001. The claim was quickly rejected by the scientific community. Considering what was learned about Mars in the years since, has your view of the claim changed?
Yeah, that's a great question. There's certainly what we've learned, not only from Mars exploration, but from additional studies of Martian meteorites, is there is organic carbon in there that's from Mars. We know that now for sure with Curiosity. We've measured Martian organic carbon now on the surface in Gale Crater, and it's there. Surprisingly, the abundances are quite high of this organic carbon, more than you would predict from meteorite input alone. We're getting a couple thousand ppm of carbon. If you do some of the calculations about how much material would come in through meteorites, you get up to like maybe 60 part per million. So we're above that. That may imply an indigenous source of Martian organic material. Now, whether it's biological or non-biological, that's a question for a later date. We don't have the tools on the Curiosity rover to answer that. The Martian meteorites we have in our collection tend to be mostly igneous rocks. So a lot of the organic carbon we believe formed at high temperature, probably from abiotic chemistry, right? Not biological reactions. And so that's why I'm really anxious for this sample return mission. We really need sedimentary rocks on Earth where you would look for fossils and preserved organic. We need that kind of material from Mars, sedimentary materials. And we just don't have much of that in our meteorite collection. So I'm hopeful that we'll be able to at least try to answer this question in 2031 when we get those cores back. We'll see.
I have a maybe somewhat novice question about just the distribution of amino acids. You obviously find tons and tons of different amino acids, but like you said, there's only 20 that are used by proteins. So are the ones that you see in highest abundance actually the ones that are used in proteins? Are they just kind of scattered throughout the samples that you see?
Yeah, it really depends on the meteorite, because we do see, I didn't have time to get into it, but meteorites have very different distributions. But if we talk about murchison, so glycine is the most abundant amino acid, and hey, that's great, right? Because it's one of the more common ones in life on Earth. But then the next highest abundant amino acid is isovaline, so which is a non-protein amino acid. So, you know, meteorites, they really have everything, I guess, and the abundances fall off the heavier they get, but there appear to be not a lot of biases there. We've detected 12 of the 20 protein amino acids in murchison, which is interesting. So we don't have everything in there. And there's a debate about where those other 8 came from. Maybe they were later on in the chemical evolutionary process. But yeah, there are 8 protein amino acids that we don't find in meteorites. That's kind of interesting. Where did those come from, right? Meteorites can't explain that. So it's got a lot, but not everything.
Cool, thank you. And I had another pretty unrelated question, but I'm curious about this circularly polarized light kind of kicking off the enantiomeric excess. I would assume that that would only work in smaller bodies where you don't have shielding from UV. So is this something that's expected to be going on actually in the parent bodies or in the earlier stages of dust growth?
Yeah, earlier stages. So icy grain chemistry, where yeah, you're exactly right. This wouldn't be something that would happen in the parent body because it's shielded from the UV. So yeah,
So
this
we
would
do.
be very early on.
So then you either need the amino acids to be present at the earlier stages, or I guess, like you said, to sort of kick it off in one of the precursors.
Exactly. So
Okay.
either inherited from the aldehyde, but again, those are only amino acids that have aldehyde precursors that are chiral, right? A lot of them are achiral. So yeah, it would imply potentially forming the amino acid on the icy grain. And actually, there's been a lot of work on that. And you can actually form quite a variety of amino acids with that icy grain chemistry exposure to radiation. So it's quite possible that could have happened then before it got incorporated into the parent body.
Yeah, if I could ask one more question about the organic matter in these meteorites, and that's return to that insoluble mass that's the majority of it. And I was sort of struck by how similar that picture looks to highly thermally mature sedimentary organic matter on Earth, right? Where you take a thermally mature organic rich sediment, yeah, it's 90+%, 99% insoluble macromolecular kerogenous stuff.
Mm-hmm.
And on Earth, we depict the production of that as a result of these kind of geopolymerization processes that result from increasing pressures and temperatures and expulsion of water and that kind of thing. But I'm just struck that a process on a meteorite, which where there's some similarities, but clearly some major differences, including the starting material probably being less complex to begin with, could result in this really similar kind of picture of this highly aromatized cross-linked stuff. Do you have any thoughts on that?
Yeah, the IOM is definitely not one of my areas of expertise. It's actually really challenging to analyze that stuff, but you're 100% right. I mean, if you look at type 4 kerogens, some of these heavily processed sedimentary rocks look very similar to the Murchison IOM. And we've done pyrolysis GCMS analyses, and you basically have the same types of fragments. And we actually even use type 4 kerogens as an analog for this meteorite material. So yeah, I don't really have an answer for why they're so similar. Does that imply the formation environment was similar or something else? It's a great question. I don't have a good answer for you, but it is interesting that they're so similar, for sure.
Great. If I can take liberty, I see we're getting near the end of our time window here. I'm going to end with one last question. So one of our goals in holding this seminar series was not only to talk about what we've learned and what the state of the field is, but also to think about what future challenges and what future advances are there going to be. So I'm going to ask a two-pronged question. One of what the answers may be the same to both of them, but I'm curious to get your thoughts. The first is just, what do you see being like, in the next 5 to 10 years, what do you see being the really exciting advances that are going to come within this area? And related to that, looking forward, is there a particular bit of information that you really want to learn? And maybe we expect to learn that in the next 5 to 10 years, or maybe that's, to the future. But in terms of, the relation of these meteorite organics to the origin of life, where do you see the field headed and where should it head?
Yeah, so both great questions. There are two areas that I think are promising. One that's happening now, and I mentioned that, the John Eiler work, where they're now doing site-specific isotopic measurements. So they're able to isolate individual carbon or nitrogen atoms in a molecule and measure the isotope ratio for those pieces. And I think that's going to be very important for really understanding the mechanism of how these things formed in the early solar system. So that's one. The other area that I would like to see more progress in, I don't know if it's going to happen in the next 5 to 10 years, are the spatially resolved measurements of amino acids and especially chirality. Some of this has been done with laser desorption techniques. They tend to favor the aromatic amino acids, but nonetheless, you can zap in very small, kind of hundreds of nanometer scale spot sizes, right? And you get that spatially resolved information. So I want to know, where are these amino acids residing? When we take a sample and we just crush it up into a powder and we do a bulk extraction, right? We can do small sample sizes, but it's not a spatially resolved measurement. So I want to know, where are these amino acids residing? Where are the chiral excesses? Perhaps there's a lot of variation. Well, we know there is in murchison, but where are those excesses? And can that provide more hints about how they formed? And so that's another area that I think could use some technology development. How do you make those spatially resolved enantiomeric measurements? And I think it'll be possible. It'll happen sometime in the future. And again, that's the benefit of having these sample return missions, because we're going to save this material. And even if we can't do it now, we're going to do it at some point in the future when that technology is ready and available. I think that answered the first part of your question. I can't remember the second. What do I hope to learn about prebiotic chemistry?
Yeah, what do you see as being the major challenge that, if you can know one thing that we don't know right now?
Yeah, so one of the things that has been bugging me, and you've probably seen some of this in the news, the detection of the protein, the extraterrestrial protein. It wasn't a non-peer reviewed journal, but there are claims that there are these really large polymers in some of these carbonaceous chondrites. And so we're actually working on that now. We've been focused primarily on free compounds that aren't bound, but we know that, like in murchison, 50% of the extract is in some sort of bound form. We intentionally acid hydrolyze it to break those components down into the free components, but there's some sort of polymer there. And we're working on methods now to look at peptides specifically. We're going to be starting that up here in the next few months. And so I hope we start learning more about, how complex these amino acids got, how long are the peptides? How could that help us maybe in our search for life as well? Can you still see me? The screen went to the last slide. Okay, yeah, I lost the picture, so I want to make sure I was still on, not talking to myself. So yeah, I think that's going to be fascinating to understand the distribution of peptides in these meteorites, if they exist, how complex, how large can they get, and how that might help guide us when we're searching for evidence of life elsewhere. I think will be really interesting. I look forward to that. And Bennu is going to help with that as well, because again, we're going to have less concerns about terrestrial contamination with those samples.
Great. All right, Denny, thank you. We're at 3 o'clock, and that was an hour and a half of fascinating stuff. Thank you so much for taking time out of your day. Again, I'll give you the Zoom single person clap. Thank you so much. This was fantastic. And a reminder to the audience, we have two more speakers, talks coming up next week. John Sutherland will be giving a talk, and then in 2 weeks, Tim Lyons from UC Riverside will be giving his talk. So please join us again next week, and thank you all for attending.
Thank you.